In this video we're going to introduce a graphical method of deciding whether an iteration of the form xn plus 1 equals g of xn will converge or not. In the previous video we saw that the equation f of x equals x to the 5 minus 6x squared minus 73, which is to equal 0, had a root in the interval of x lying between 2 and 3, that the equation x to the 5 minus 6x squared minus 73 equals 0 could be rewritten in an x equals g of x format as x equals the fifth root of 6x squared plus 73, or as x equals 6x squared plus 73 all divided by x to the power 4, or as x equals 73 divided by x times by x cubed minus 6. We also saw that the iteration x1 equals 2.5 and xn plus 1 equals the fifth root of 6xn squared plus 73 converged rapidly to the value of alpha. But we also saw that the other rearrangements of the equation into the x equals g of x format led to iterations that did not converge to a root. And in this video, the convergence or otherwise of iterations of the form xn plus 1 equals g of xn are going to be investigated in a graphical diagram. So our first step in producing these graphs is to start by drawing the graphs of y equals x and y equals g of x. The root of the equation x equals g of x corresponds to the point of intersection of these two graphs, and we should start by marking the number x1, the starting value for the iteration, on the x-axis. We should move vertically from the point x1, 0 to the curve. Now if we move up to the curve vertically from the point x1, 0, we're going to arrive at the point x1, g of x1. But since we are using the iteration xn plus 1 equals g of xn, the point x1, g of x1 is exactly the same thing as the point x1, x2. The next step is to move horizontally from the point x1, x2 until we meet the line y equals x. And if I'm moving horizontally, then the x coordinate is going to change, the y coordinate stays the same, but I'm only moving as far as the line y equals x, so that means the x coordinate and the y coordinate will be the same, which means that we will have arrived at the point x2, x2. The next step is to move from the last point, which will be of the form xk, xk. In this case it's the point x2, x2. We've got to move vertically from this point to meet the curve. And that's going to give me, in this case, if I move vertically from the point x2, x2 to meet the curve, it's going to give me the point x2, g of x2, which, because we're using the iteration xn plus 1 is g of xn, that gives me x3 is the same thing as g of x2. So the point that I move down to is the point x2, g of x2. In other words, it's the point x2, x3. We must then move horizontally to the line y equals x, and moving horizontally again will keep the y coordinate fixed, the x coordinate will change, so we're going to end up at the point x3, x3. Now we should repeat step 3 until we can see what's happening. So again, from the point x3, x3, I'm going to move vertically to the curve, which gives me the point x3, x4, and then horizontally back to the line, which is going to give me the point x4, x4. We can see the iteration is spiraling in to the point of intersection of y equals x and y equals g of x. So the iteration is converging to the point alpha, alpha, where alpha is a root of the equation x equals g of x. So the diagram that I've drawn here illustrates the iteration x1 equals 2.5. xn plus 1 is the fifth root of 6xn squared plus 73. So to start with, I've drawn the graph of y equals x, and I've drawn the graph of y equals 6x squared plus 73 to the power 1/5, which is exactly the same thing as the fifth root of 6x squared plus 73. Our starting value is 2.5. So we start with the point x1, 0, which is 2.50. We move up to the curve, and then we move across to the line. If we zoom in to the area around the point of intersection, we'll be able to see the progress of the iteration rather more clearly. Starting from the point 2.50, we move vertically upwards until we meet the curve, which will be at the point 2.5 g of 2.5. In other words, that is the point x1, x2. From this point, we move horizontally across to the line, which will again give me the point x2, x2. Vertically to the curve will give me the point x2, g of x2. In other words, the point x2, x3. Horizontally to the line will give me the point x3, x3. And then vertically upwards would then give me the point x3, x4. Now in this case we can see the iteration is giving us a staircase type diagram, which staircases in to the point of intersection of y equals x and y equals g of x. So the diagram is telling me that the iteration is converging to the point alpha, alpha, where alpha is the root of x equals g of x. It's worth having a look at how critical the starting value for the iteration is. In the screenshot we've got at the moment, we've got the starting value has been changed from x1 equals 2.5 to x1 equaling 0. And we can see that the staircase diagram is still converging nicely to the root of the equation x equals g of x. And if we start the video, we can see that that continues to be the case. There's very little difference on terms of the values of the iteration all the way up to the solution point, and even if we go beyond the solution point, all that starts happening is the iteration staircases down to the point of intersection. So what this is telling us is that provided the initial value of the iteration, x1, is reasonably close to the root, the iteration will actually succeed in finding the root in this particular case. Now this new diagram illustrates one of the other iterations that we were looking at. It illustrates the iteration x1 equals 2.5, xn plus 1 equals 6xn squared plus 73 all over xn to the power 4. So starting with our first value of x1 equals 2.5, we move up to the curve to obtain the point x1, x2, across to the line to obtain the point x2, x2, vertically to the curve to obtain the point x2, x3, horizontally to the line to obtain the point x3, x3, vertically to the curve to obtain the point x3, x4, horizontally to the line to obtain the point x4, x4, vertically to the curve to obtain the point x4, x5, horizontally to the line to get the point x5, x5, and vertically to the curve to get the point x5, x6, and you can see that this is way off the screen. So in this case, the iteration is spiraling out or cobwebbing out from the point of intersection of y equals x and y equals g of x. So we can see that the iteration does not converge to the solution of x equals g of x. So we'll now consider another example where we are considering the equation e to the 0.2x, take away x, take away 4 equals 0. First thing we've got to do is we've got to use the diagram that shows the graphs of y equals x and y equals e to the 0.2x, take away 4, to determine the number of roots of the equation. So the equation e to the 0.2x minus 4 equals 0 can be rewritten as x equals e to the 0.2x, take away 4. So the roots of the equation we've called equation 1 are given by the points of intersection of y equals x and y equals e to the 0.2x, take away 4. And from the graph we can see that there are certainly 2 points of intersection within the interval -5 to 15. There won't be any more solutions because if x is less than -5, then that certainly tells me that x is smaller than -4, but e to the 0.2x take away 4 is always at least -4. If x is bigger than 15, then the gradient of e to the 0.2x take away 4 is certainly bigger than 1. So e to the 0.2x take away 4 is growing at a quicker rate than x is growing. So there's certainly not going to be any more points of intersection beyond x equals 15. We now know that equation 1 has 2 roots. And we've got to prove that one of these roots lies in the interval 14 is less than or equal to x is less than or equal to 15. So if we let f of x equal e to the 0.2x minus x minus 4, then f of 14 is minus 1.56, f of 15 is 1.09, and since f is simply a combination of an exponential function and a polynomial, we can certainly say that f is continuous. So we've got sign change in a continuous function tells me that there is a root in the interval 14 to 15. We've now got to consider the iteration x1 equals 14, xn plus 1 equals e to the 0.2 xn, take away 4. And we've got to use the diagram to determine whether this iteration will help find a root of the equation 1. And if the iteration will, then we've got to use it to find the root of equation 1. So we need to start by marking the point x1, 0 on the x-axis and moving vertically up to the curve, which will now give me the point x1, x2. Moving horizontally to the line y equals x gives me the point x2, x2. Moving vertically to the curve will give me the point x2, x3. Horizontally to the line y equals x will give me the point x3, x3. Vertically to the curve gives me the point x3, x4. Horizontally to the line will give me the point x4, x4. Vertically to the curve will give me the point x4, x5. And then horizontally to the line again will give me the point x5, x5. And we can see that this iteration is actually converging to the negative root of f of x equals 0. If we now use the iteration on our calculators, we've got x1 equals 14, x2 equals 12.445, x3 is 8.048, etc. And if we go through until it settles down to 3 decimal places, we'll see that x9 and x10 are both minus 3.504. So the equation f of x equals 0 has a negative root at x equals minus 3.504. If we now look at the same iteration, xn plus 1 equals e to the 0.2 xn minus 4, but with a starting point of x1 equals 15, then we get something quite significantly different. So marking the point 15, 0 on the x-axis and moving vertically to the curve, we obtain the point x1, x2. Moving horizontally to the line y equals x, we obtain the point x2, x2. Vertically to the curve will now give us the point x2, x3. Horizontally to the line will give me the point x3, x3. And then vertically we're going to go way off the axes. So in this case we can see that the iteration is going to staircase away from the positive root, and in fact the values are just going to get larger and larger without giving us anything useful at all. Going back again to the equation e to the 0.2 x minus 4 equals 0, we've got to rewrite this equation in the form x equals a times the logarithm of x plus b. Well, starting with equation 1, if we isolate the e to the 0.2x term on the left hand side, then we'll obtain e to the 0.2x equals x plus 4. Taking natural logarithms of each side gives me 0.2x equals the natural logarithm of x plus 4, and multiplying up by 5 gives me x equals 5 times the natural logarithm of x plus 4. So this suggests that we might try the iteration x1 equals 14.5, because we know that the positive root is somewhere between 14 and 15, and then xn plus 1 equals 5 times the natural logarithm of xn plus 4. So using this iteration on my calculator, I obtain the following values of x2, x3, x4, etc. And we can see that this is rapidly converging to a value which is approximately 14.621. So that's suggesting that equation 1 has got two roots, namely minus 3.504 and 14.621. If we want to check that these two roots are actually correct, then if we check using the sign change in a continuous function, then we can check that there's a sign change in between minus 3.5045 and minus 3.5035, which will then ensure that I've got a root in which is minus 3.504, correct 3 decimal places. And similarly, I can check that there's a sign change in the continuous function between 14.6205 and 14.6215, which will ensure that I've got a root which is 14.621, correct to 3 decimal places. That concludes our look at using graphical methods to investigate the convergence of iterations of the form xn plus 1 equals g of xn.